time. So I originally gave this talk as part of the Caltech astronomy outreach program, and that was a shorter talk. So I have more time now with this talk. So I added a small section at the end, and yeah, I also have more time for questions. Okay, beginning in 1200 BC, a mysterious apocalypse happened that completely destroyed the Mycenaean civilization. We don't know what the apocalypse was or what caused it. We do know from inscriptions that the inscriptions talk about the Sea Peoples, which is a confederation of nomadic peoples that attacked Egypt and probably other cities in the ancient Mediterranean around 1200 BC. We know from the archaeological record that the inhabitants of Mycenaean Greece were strengthening their already formidable walls. So obviously they were afraid of something. We also see from the archaeological, well, we also see from the literary evidence that the kings were writing letters to each other, begging for military aid. But if the military aid ever came, it wasn't enough. Because from 1200 to 1100 BC, almost every single city in the Eastern Mediterranean that was not in Egypt burned to the ground. You see that in the fire signs, all around the Mediterranean. So in this 100-year period, the population of the Mycenaean Greek cities, well, the population of Mycenaean Greece crashes by 90%. There was a drastic reduction in material prosperity. Instead of this nice ornate pottery, you had this, not so nice pottery. Instead of pottery being found all across the Mediterranean, pottery is now very localized. If a style is invented in Athens, it stays in Athens. It doesn't even go to Sparta, for example. Even more dramatically than all of that, writing was completely lost. And along with it, any historical memory of the Mycenaeans. When the Greeks re-emerged into civilization, they know nothing about the Mycenaeans. Okay, so around 800 BC, the Greeks emerged out of the Dark Ages and into the light of a brave new world. This world was completely different. They no longer lived under all-powerful kings ruling by divine right, which is the overwhelmingly dominant form of government throughout history, all over the world. Instead, they lived in a collection of thousands of different city-states. Each of these city-states, which you can see on the map, had their own government, their own military, and their own foreign policy. So this allowed a level of intellectual freedom that was unprecedented. Because if the Athenians didn't like what you were saying, if they were offended because you were denying the existence of their gods, that's fine. You could move to, Miletus. If the Milesians also hated you, you could move to Ephesus or Alexandria or one of the many, many other cities. Well, not Alexandria at that time, but probably one of the cities over here, as we'll talk about. Okay, so as I said, the Greeks lost their writing system. Instead of this Mycenaean script that they used to use, they adopted the Phoenician writing system. But they didn't just copy it. They did something characteristically Greek, which is they took the Phoenician writing system, which is kind of like an alphabet, but without the vowels, and they added the vowels. And thereby they invented the first alphabet in history, which became the ancestor of all European alphabets. But 800 BC was not yet a time for science. It was still a time of myth. Question? Okay, yeah, it was still a time of myth. Now, myth comes from the ancient Greek word mythos, meaning a story or a tale or a legend. You can see an example of mythos over here. This is from Hesiod's Theogony, or the birth of the gods. First of all, chaos came into being, but then Gaia, broad-chested, always the unshakable seat of all the immortals, who hold the peak of snowy Olympus, and dark Tartarus in the recesses of the wide-weight earth, and Eros, the most beautiful among the immortal gods. Okay, so how did the universe came into being? Well, one god gave birth to another god, and so on and so forth, until you have all of these gods representing all of these different aspects of nature. Okay, so how does Hesiod know all of this? He just does. It's not because he went out and he formed a hypothesis and he took measurements and he applied the Pythagorean theorem. No. He knows all of this because it's a tradition of his people. It's what they've always believed, and so that's what he believes. If the Greeks were just any other civilization, their intellectual history would have begun and ended with myth. Well, but the Greeks were not an ordinary civilization. They were absolutely extraordinary. Beginning in the 7th century BC, they started to develop another way of understanding the world. They came up with logos, which is logic or rationality. The first philosopher we hear about to apply this approach was Thales of Miletus. Thales came from this city over here, Miletus. He thought that the origin of all reality, or the arche, is water. Okay, that's not exactly true, but he was the first philosopher ever, so let's cut him some slack. He also supposedly predicted a solar eclipse in 585 BC. We now know that this was impossible. He did not have the knowledge to do this. So if he did it, he must have gotten really lucky. He also was reputed to have discovered static electricity. And he did something that's also characteristically Greek. He learned from Egyptian and Babylonian mathematics, which at the time were the most advanced in the world, because these civilizations were, at the time, much older and much wiser than the ancient Greeks. But he wasn't happy to just learn from, his betters. He took their results, which they discovered empirically, and he proved them in a rigorous mathematical way. And that's how mathematics is supposed to be done. That's how modern mathematics is done. You don't do it by experiment, you do it by proof. Now, my favorite story about Thales is that he was the first absent-minded professor. So one day he was walking in the city, but he wasn't paying attention to where he was going. He was looking up at the stars. So he was walking like this, and he tripped and he fell down a well. Happily for him, there was a slave girl who was right beside the well who happened to see him fall. So she rescued him from the well, and then she mocked him, saying, "You philosophers, you're so crazy. You're so obsessed about what happens in the sky that you don't know what happens at your very feet." There you go, the absent-minded philosopher. Okay, so the first great astronomer that we hear about is Anaxagoras of Clazomene. Clazomene is right over here. He is another one of the Ionian philosophers. He believed that the Earth is a flat disk suspended on air, which for ancient civilizations was not an uncommon belief. He thought that the sun is a hot stone the size of the Peloponnesus. This was an unusual belief because most ancient civilizations believed that the sun, the moon, and the celestial bodies were gods. And Anaxagoras, for his trouble, he got banished from Athens because they charged him with impiety. Now, most modern historians think that the real reason he was banished was not because of his astronomy. It's because he was friends with Pericles, who was then the leader of democratic Athens. Now, there was an interesting feature of democratic Athens, which is when anything goes wrong, and sometimes when nothing goes wrong, they blame it on the leader, and they expel the leader, they ostracize the leader. And they ostracize everybody associated with the leader. Well, Anaxagoras was a friend of Pericles, so he got the blame, and he had to flee for his life to Lampsacus. Anaxagoras also developed the first correct explanation for lunar and solar eclipses. And he thought of the moon as a world like ours, with plains, ravines, and even people on it. As far as I know, he was the first person to speculate about the existence of alien life. Okay, from Anaxagoras, we move on to the Pythagoreans. The Pythagoreans, or a mathematical cult. That's not something you see every day. It was founded by Pythagoras of Samos. Samos being an island off of the coast of Ionia. And the Pythagoreans believed that the whole numbers are the building blocks of all reality. For that reason, they believe that numbers are holy, especially the number 1, presumably because from the number 1, you can build up to every other number. They believed in the transmigration of the soul, very reminiscent of Hinduism. They were vegetarians. They believed in gender equality, which for the time would have been pretty weird and crazy. And they also hated beans. Legend had it that Pythagoras had to run for his life. But in order to make any more progress, he would have had to cross a bean field. Well, he couldn't do that. So he didn't. And so he got caught, and that's how his life ended. Now, most people today probably know the Pythagoreans from the Pythagorean theorem, which is a squared plus b squared equals c squared when you have a right triangle. Okay, so look at this right triangle. What happens when a equals to 1 and b equals to 1? Well, c is going to be equal to the square root of 2, right? And what do you know about the square root of 2? It's irrational. An irrational number cannot be expressed as a ratio of 2 whole numbers. So very ironically, the Pythagorean theorem leads you to construct a number that falsifies the entire premise of the Pythagorean belief. And even more ironically, who was it that discovered the phenomenon of irrationality? It was the Pythagoreans. Legend has it that the Pythagorean who proved that the square root of 2 is irrational, he was so threatening to the Pythagorean belief that they killed him. They threw him into the ocean because they didn't want him destroying the basis of their beliefs. Okay, so the Pythagoreans also had interesting astronomical beliefs. They were the first people we know of to think that the Earth is a sphere. They thought that the planets were held on crystal spheres, making music as they orbited. They also thought, and they were also the first people we know of to think this, that the Earth is not the center of the universe. They gave that place to a central fire. Now, notably, the central fire is not the sun, because they thought that the sun also orbited the central fire. Unfortunately, we have no idea how they came to these beliefs. Was it, logically, or was it by for superstitious or religious reasons? We just don't have the records to know. Okay, fortunately, we know of a lot of other ancient Greek scientists who believed in the round Earth. By the 5th century BC, Aristotle of Athens had become the greatest scientist of antiquity. And in his book on the heavens, he gives 5 reasons for why the Earth must be a sphere. Now, these are not his arguments. He's summarizing other people's arguments. And he's summarizing them in a way that implies, this is common knowledge. Everybody knows this already. I'm just restating the obvious. Okay, so what is this obvious thing that he's restating? Well, number 1, for every portion of Earth has weight until it reaches the center. So Aristotle believed that the center of the Earth is the center of the universe. And everything in the universe, from Earth to water to air, tries to sink to the center, tries to get as close to the center as it possibly could. Now, if the Earth was any shape other than a sphere, then some pieces of the Earth will be farther away from the center than it has to be. So that piece is going to flow, it's going to move, until that's no longer the case. And the only shape where every portion of the shape is as close to the center as it can possibly be is a sphere. Now, Aristotle's theory of gravity is incorrect. It turns out that the Earth is not actually the center of the universe, but his explanation for why the Earth is a sphere is entirely correct. If you ask any modern physicist why planets are round, they're going to give you a very similar answer. They're going to call it hydrostatic equilibrium or whatever, or minimizing potential energy or whatever fancy term that they use. But the physical reason is exactly as Aristotle stated it. Okay, now reason number 2.
Very interesting.
Yeah, do you have a question or just a comment?
Michael, I have a question.
Sure.
Pythagoreans.
Uh-huh.
Had the concept of zero been invented already at the time of the Pythagoreans?
No, it hasn't. And the ancient Greeks would never come up with the concept of zero. I think the first people to come up with it were actually the Indians. And from there, it diffused to the Arabs and it diffused to Europe. But I'm not exactly sure of that progression. But yeah, like nobody will come up with zero until many, many centuries afterward.
Okay, thank you.
Okay, moving on. Now, reason number 2. How else would eclipses of the moon show segments shaped as we see them? Okay, very good point. Number 3. There is much change, in the stars which are overhead, and the stars seen are different as one moves northward or southward. So from any point on the Earth's surface, if you look at the stars at night, they seem to circle counterclockwise about an imaginary point. And the elevation of this imaginary point above the horizon is equal to your latitude. Okay, number 4, the case of elephants, a species occurring in each of these extreme regions, suggesting that the common characteristic of these extremes is explained by their continuity. Okay, so in ancient times, there were elephants in both modern-day Morocco and modern-day India. So Aristotle was thinking, what if the reason that there were elephants in both of these places, but not in between, is because Morocco and India are connected on the other side of the globe? Well, he didn't know that these elephants were actually 2 different species. And he also didn't know that Morocco and India were actually, they're actually not that far apart compared to the side of the Earth. Interestingly, Aristotle did have a somewhat good idea of the side of the Earth. He says, those mathematicians who try to calculate the side of the Earth's circumference arrive at the figure 400,000 stades. This indicates not only that the Earth's mass is spherical in shape, but also that as compared with the stars, it is not of great size. Now, 400,000 stades is about 70% too big, but it's close enough to the right answer that the mathematicians couldn't have just guessed. They had to have an actual method of measuring the side of the Earth. Unfortunately, we don't know who these mathematicians were, and we have no idea how they came to their measurement. Okay, so Aristotle was the last great scientist of the age of the city-states. In the mid-4th century BC, King Philip of Macedon, over here, came up with ingenious new military tactics. They involved the use of extremely long spears in a phalanx formation, combined with new uses of cavalry. And using these ingenious combined arms tactics, he managed to take over essentially all of the city-states of ancient Greece, including the great cities of Athens and Thebes. Okay, so his son was Alexander the Great. I should say that Philip of Macedon was assassinated, and we don't know who assassinated him or why he was assassinated. But whoever assassinated him probably thought that his son was going to be not half as bright as his father was. Well, unfortunately, his son happened to be Alexander the Great, one of the greatest military geniuses of all time. So instead of conquering just, out of ancient Greece, he conquered Persia, which for centuries had been the nightmare of the Greeks. He conquered Egypt, which had itself recently been conquered by Persia. And he went all the way to the Indus River in modern-day Pakistan, contemporary India. So Alexander didn't leave any heirs. Upon his death, his generals divided up his empire into 3 portions. There's the Antigonid Empire, covering modern Greece. There's the Ptolemaic Empire, covering basically Egypt. And there's the Seleucid Empire, covering the Middle East. Okay, so Alexander founded the city of Alexandria. The first ruler of Alexandria, Ptolemy I, would found the great library of Alexandria. And that will be a center of learning for centuries to come. One of the scholars that Alexandria attracted was Eratosthenes. Now, Eratosthenes was a native of Cyrene, which is a Greek colony in modern-day Libya. But he got invited to work at the Great Library of Alexandria. He accepted, and he was so good that he rose up the ranks to become chief librarian. So one day, while he was reading through the scrolls at the Great Library, he encountered a scroll that said that on noon of the summer solstice, the sun shone directly down a well in the Egyptian city of Syene, which is due south from Alexandria. Now, Eratosthenes lived in Alexandria, so he knew that this wasn't the case in Alexandria. The sun is not directly overhead. So he waited until the next solar summer solstice. He put a stick into the ground at exactly noon, and he measured the length of the shadow that it cast. From the length of the shadow and the length of the stick, he could calculate this angle, alpha. And this angle, if you do some geometry, is exactly the same as this angle over here. The angle between Alexandria and Syene as measured from the center of the Earth. And this angle turns out to be 7.2 degrees, or 1/50th of a full circle. Now, Eratosthenes also knew from Egyptian government records that the distance from Alexandria and Syene is 5,000 stadia. So if 1/50th of a full circle is 5,000 stadia, then the full circumference must be 50 times 5,000 stadia, or 250,000 stadia. Now, we don't know which stadium he used, because there were multiple for different places. But if he used the Egyptian stadium, he will be only 1% off from the right answer. If he used the Olympic stadium, it will be 20% off. But even 20% off is extremely good for 200 BC. Okay, and by the way, it's especially impressive considering that at this time, every other ancient civilization believed that the Earth was flat. There was no other ancient civilization that ever discovered the Earth was spherical. Okay, that itself is pretty impressive, but that was by far not the most impressive thing the ancient Greeks did. They also tried to measure the distance and size of the sun and the moon. The first person we hear about to do this was Aristarchus of Samos. Samos being an island off the Ionian coast. Okay, so here's how he did it. During a lunar eclipse, the moon crosses the Earth's shadow. Now, if you could measure how long it takes for the moon to completely disappear, and you could measure how long it takes for the moon to completely cross the shadow, the ratio between the two is exactly the ratio between the moon's diameter and the Earth's diameter. And if you know how big the Earth is, which they did, then you can calculate how big the moon is. Okay, so once you know how big the moon is, you can calculate how far away it is, because you know how big it appears in the sky. And the distance of the moon is just the diameter of the moon divided by the apparent angular diameter. Once you know how distant the moon is, you can calculate how far away the sun is. Because consider the situation a quarter moon. A quarter moon, exactly half of the moon is illuminated, and half of the moon is in the dark, is at night. So this angle over here has to be 90 degrees. Now, if this angle over here is 90 degrees, and you could measure this angle over here, the angle between the sun and the moon as seen from the Earth, then you could use trigonometry to get the ratio between L and S, between the lunar distance and the solar distance. And since you know the lunar distance, you can get the solar distance. Now, I make it sound simple, but number one is actually a lot more complicated. But even so, high school geometry is enough to solve this problem. So I leave it as an exercise for the listener. But the other complication that we don't have, but the ancient Greeks did, was that they didn't have trigonometry. Aristarchus had to invent a lot of trigonometry just to be able to do his astronomy problem. But he was very smart. He was very good at geometry, and he did the necessary invention to be able to solve this problem. And here's what he got. He actually got a pretty good number for the radius of the moon, but his other numbers were way off. He thought that the moon was 20 Earth radii away when it's actually 60. And he thought that the sun was 7 times bigger than the Earth when it's actually 109 times bigger. But you can see that even with his drastically underestimated numbers, the solar system is very big. And not only that, the sun is much, much bigger than the Earth. Perhaps inspired by his numbers, Aristarchus became the first person to propose the heliocentric hypothesis. Here's what Archimedes says about it in his book, The Sand Reckoner. Aristarchus of Samos brought out a book consisting of some hypotheses in which the premises lead to the result that the universe is many times greater than that now so-called. His hypotheses are that the fixed stars and the sun remain unmoved, that the Earth revolves around the sun in the circumference of a circle, the sun lying in the middle of the orbit. Okay, so this is clearly and without any doubt a heliocentric model. But there's a problem with any heliocentric model, and that's a problem of stellar parallax. Now, parallax is a phenomenon where objects appear to be in different places depending on your viewpoint. So you can demonstrate parallax just by holding out a finger in front of your eyes and closing one eye and then closing the other eye. And you can see that the position of your finger seems to vary depending on which eye you have open. Now, if you apply that to the Earth going around the sun, if the Earth is moving, then the stars should appear to be in different positions, depending on where you are in the Earth's orbit. Well, the ancient Greeks tried to detect stellar parallax. They failed. And therefore, from the failure, you can have 2 possible explanations. Number one, you can say that the stars are very far away. So parallax exists, but it's undetectable. That's what Aristarchus believed, because he believed in heliocentrism. Or you can take the simpler explanation, and you can say that the Earth is not actually moving; it's staying still, and that's why you don't see parallax. That's the explanation given by Aristotle, and Aristotle was the greatest scientist of antiquity, so his word became the scientific consensus. Okay, parallax is not just an annoyance. It's an essential tool of astronomy. Whenever you see an astronomical distance, if it's greater than 1 light year, I can guarantee you that parallax was used to measure that distance. If not directly, then at least indirectly. So given the central importance of parallax to modern astronomy, It's very fitting that the first person to apply a parallax to calculate astronomical distances was the greatest astronomer of antiquity, Hipparchus of Nicaea. Hipparchus's accomplishments are way too numerous to list. He's called the father of trigonometry for coming up with the first sine table. He invented the magnitude system that astronomers still use today. He discovered the precession of the equinoxes. He came up with the stellar catalog. He was one of the first people to apply numbers, to put numbers to models, and thereby make astronomy a quantitative science. Okay, but aside from all of those great accomplishments, he also used parallax to calculate the size and distance of the moon. So here's the very simplified version of the concept. There was a total solar eclipse. It was total as seen from the Hellespont, but it covered only 4/5 of the moon as seen from Alexandria, which was 1,100 kilometers away. Now that means that this angle right here must be 1/5 of a solar diameter, or 0.11 degrees, because the position of the moon is 0.11 degrees discrepant between these two locations. Now, 0.11 degrees corresponds to 1,100 kilometers in this triangle. So you can use trigonometry to figure out that this distance must be 570,000 kilometers. Since you know how big the moon appears in the sky, it's about 1/2 degree, you can use the distance to calculate the radius of the moon. Now, that was a very simplified and hand-wavy approach, but if you know anything about ancient Greeks, they were very good at astronomy. So they didn't use a very simplified and hand-wavy approach. They did it rigorously and properly. So this is also left as an exercise for the listener. Okay, so he actually got pretty good values. Here's what Ptolemy says in his Almagest. With respect to the sun, not only so that's about the sun. Let me talk about the moon first. He said that the moon was about 1/3 the radius of the Earth, which is almost exactly correct. He thought that the moon was 67 Earth radii away. It's actually from 56 to 64 radii away. So that's also very close. But with respect to the sun, he tried to measure the parallax of the sun and he failed. As Ptolemy said, with respect to the sun, not only the amount of its parallax, but also whether it shows any parallax at all is altogether doubtful. So from the failure to measure the solar parallax, Hipparchus concluded that the sun must be more than 490 Earth radii away. And from this lower limit on the distance, he concluded that the sun must be at least 12 times bigger than the Earth. The actual value is 100 times. Okay, so Hipparchus' solar system is even bigger than Aristarchus's. He thought the sun was even bigger than Aristarchus thought it was. But Hipparchus, as far as we know, was not a heliocentrist. Okay, so the last great ancient astronomer of antiquity was Ptolemy of Alexandria, who lived and grew up and worked in what was now Roman Egypt. Ptolemy wrote the Almagest. The Almagest is Arabic for the greatest, because the medieval Arabic astronomers who translated him thought that he was the greatest astronomer of all time. Ptolemy summarized the accomplishments of Apollonius, Aristarchus, and Hipparchus, and he also introduced his own geocentric system for the sun, the moon, and the planets. This is a system with epicycles, equants, and deferents. So here's how it works. If you just use a very simple, the simplest possible geocentric system, you say that all of these solar system bodies, they move around the Earth in a circle at uniform speed. The problem with that model is that it's obviously wrong. Because if you just look at the planets, they don't even always move in the same direction. Sometimes they speed up, sometimes they slow down, and then stop, and then reverse direction, and then stop again, and then reverse the direction a second time to resume their motion in the original direction. So the simplest possible geocentric model is obviously wrong. Now, to account for that, you can add an epicycle. So in this model, the planet orbits an imaginary center, and this imaginary center orbits the Earth. Both of these motions are uniform and circular, but the combined motion as seen from the Earth is no longer uniform or necessarily circular. Okay, but Ptolemy noticed that this still wasn't accurate enough. It still did not match observations to the limits of observational error. So he added something else called the equant. Under this model, the center of the epicycle doesn't orbit the Earth, but it orbits this point labeled by the X. Now, the motion of this epicycle is uniform as seen from the equant, but it's not uniform as seen from the Earth. And if you think that this system is really ugly and nonsensical and clumsy, the ancient Greeks would have agreed with you. Ptolemy would have agreed with you, but nobody could do any better. So this became the standard model for the next 1,500 years. Okay, so if Ptolemy was the pinnacle of theoretical ancient astronomy, the Antikythera mechanism was the pinnacle of ancient Greek practical or applied astronomy. The Antikythera mechanism is an analog computer. We know of nothing like it from anywhere in the ancient world. The history of the discovery of this device is pretty fascinating. Around 70 BC, the ship that was carrying this device to a destination unknown encountered a severe storm in the Aegean Sea. Like ships throughout the ages, when they encounter the storm, they try to take shelter behind the island of Antikythera, which is marked on this map over here. But unfortunately, it was not enough. The storm was too severe, it destroyed the ship, and the entire cargo sank to the ocean floor. In the year 1901, there was a Greek ship that encountered another storm in the Aegean Sea. And this ship also took shelter behind the island of Antikythera. This ship had sponge divers on board. So while they were taking shelter, or I guess like shortly after the storm passed, they sent the divers down to the ocean floor. And they were absolutely shocked by what they found. They found what they thought were naked dead bodies. So then after they came up, their colleagues went down and did further investigations. It turns out that they were not actually naked dead bodies, they were ancient Greek statues. But aside from the statues, they also found coins, they found amphorae, which are containers for olive oil, and they found hunks of metal that we now know as the Antikythera mechanism. This was in 1901. For more than 100 years, the Antikythera mechanism sat in a museum. Nobody had the technology to peer inside and figure out how it worked. Well, in 2008, that changed. A team from Cardiff University used modern techniques, namely X-ray tomography and high-resolution surface scanning, to look inside the mechanism. They could see more than 30 years. They could read hundreds of different inscriptions. And if you just look at this visually, it's hard to see how you could read any inscriptions. But with modern techniques, it's possible. So in 2008, for the first time, we had a really good idea of how this device worked. It contained more than 30 gears in a complex gear train that had neither precedents nor descendants in the ancient world. There will never be something this complicated until the 14th century in medieval Europe. If you look at the ancient world, they had devices with gears in them, but they were very simple. They were something like odometers on carriages. they will have maybe 3 to 4 gears in a very simple configuration, not 4D. Okay, so the anti-Kildare mechanism calculates the positions of the sun, the moon, and the planets. It shows you the date on 2 different calendars. It tells you which games are happening in any given year. It calculates the phase of the moon. And most impressively of all, it predicts the date and time of solar and lunar eclipses. Okay, so let's see the mechanism in action. Okay, I'm gonna try to slow this down. I didn't succeed the last time. Let's see if I succeed this time. Okay, no, I can't, well, yeah, I can't slow it down, but whatever. I'll just talk. Okay, I'll just talk fast. So there's a hand crank. You crank the hand crank and that advances time. And by advancing time, there are dials on the front face that rotate to indicate the positions of the sun, the moon, and the 5 planets. Now, it turns out that the solar system is basically flat. So you only need 1 dimension to approximately tell you where all of the objects are. Okay, so there's 1 dial for the sun, which is over here. There's 1 dial for the moon, and there's a dial for the planets, for each of the planets. Yeah, my favorite part of the mechanism is this little ball over here. It's a half silver sphere, and it rotates to indicate the phase of the moon. So here, that's new moon, and here is full moon. Now, along this outer rim, you see inscriptions. The inscriptions indicate the month and date in the Egyptian solar calendar. And I think on the outer rim, it indicates the zodiac signs. So that's how you know where all of the planets are. If you look at the inner rim, these represent the days of the month in the lunar calendar. You read it by looking at the dial for the moon and yeah, reading off the date from which date it overlaps. Okay, so look at the motion of these dials. You're going to see that the motion of the sun and the moon is basically uniform. But the motions of the planets are not in any way uniform. They speed up, they slow down, they reverse direction, they do all kinds of weird and crazy things. Just like the planets in the real sky. So now it's going to take apart the mechanism to show you the guts. So there's a different disk for each of the celestial objects connected to a pointer. Yeah, this is a speculative reconstruction. The planets are a lot more speculative than the sun and the moon, because we think we pretty much know exactly how the moon and the sun calculations are done. Okay, so there's a separate gear train for every celestial object. Okay, Jupiter, Mars. There's going to be one for the sun and the moon. Although I don't think this video shows the moon explicitly. Okay, you see lots and lots of very intricate gears. Okay, and there's even a backside to this mechanism. Now, the backside has 2 big dials and a few smaller dials. Let's look at this big dial on the left. This is a calendar display. This shows something called the Metonic cycle, which is 19 solar years. And it turns out that that's almost exactly 235 lunar months. Because of this equivalence, the Metonic cycle was the basis for a lot of ancient calendars, including the calendar of Corinth. So along this spiral, you see 235 different inscriptions indicating the name of the month in the Corinthian calendar. It was a bit too much to try to fit 235 names on one circle, which is why they have a spiral and they have a pointer that advances along the spiral to tell you which layer of the spiral you should be reading. When you get to the end of the spiral, you have to lift the pointer and manually reset it to the starting position. Okay, so this spiral advances like this. On the top, you see a smaller dial that indicates your position in a 4-year cycle. The ancient Greeks had a lot of games that happened once every 4 years, including most famously the Olympic Games. So in each of these 4 positions, there are inscriptions that tell you which games are happening this year. Now on the right, you have the eclipse predictor. This shows you something called the Saros cycle, which is 18 years, I think 10 months and some odd days. I forgot the exact number, but it's exactly 223 lunar months. And it turns out that if you have an eclipse today, for example, then you're very, very likely to have another eclipse exactly after 1 Saros cycle. So in this way, you can predict eclipses. Okay, so this pointer shows you your position within the Saros cycle, and you see inscriptions. These inscriptions tell you that an eclipse might happen on this date. It tells you the exact date and time of the eclipse, and it tells you the type of eclipse. Is it lunar or is it solar? Now, 1 Saros cycle is exactly 223 lunar orbits, but that turns out to be not an integer number of days. It's an integer number of days plus 8 hours. So after 1 Saros cycle, even though there's going to be an eclipse, it's going to be 8 hours later from the current eclipse. 2 Saros cycles later, the eclipse is going to be 16 hours later, and 3 Saros cycles later, it's going to go back to the original time. So this smaller dial over here tells you whether you should be adding 0 hours, 8 hours, or 16 hours to the time of the eclipse. Okay, yeah, so to read the dial, well, to predict the eclipse, you wait for the dial to overlap one of the inscriptions. You add the time that's elapsed in the Saros cycle to the beginning of the cycle, and then you add the time indicated by this small dial. Okay, so that's the eclipse predictor. This just recaps all of the cycles that I told you about. Metonic cycle, the eclipse cycle, which is 4 times the Metonic cycle. Yeah, there's an eclipse predictor. Yeah, and here you see the gear that's driven by the hand crank. And here you see the main gear called the input wheel, called the mean sun wheel. And this is the biggest gear of the whole device. And this is actually the gear that you see on all of the pictures. So let's wait a while and it's gonna show you. Okay, there. So this thing over here is a mean sun gear. Now this model was reconstructed by Michael Wright. It was a great feat of genius just to reconstruct it from all of the fragmentary evidence, because we don't have the whole device. We have maybe half the device, and even the half of the device that we have is in like dozens of fragments. The picture I showed you is only the biggest fragment. Okay, so what are the mechanisms underlying the workings of the device? Well, it's pretty ingenious. When you have stacked gears, namely one gear on top of the other, you can do addition. The gear at the bottom could be turning at one rate, and the gear at the top could be turning at another rate relative to the gear at the bottom, in which case the gear at the top will be turning at the sum of the 2 rates relative to absolute space. So with gears, you can add rotation rates. Now you can also multiply and divide rotation rates. If you look at this contraption over here, imagine that you're using a hand crank to crank gear number 1. Now gear number 2 is going to make 2 rotations for every rotation of gear 1. So in this way, you can multiply rotation rates. By changing the ratio of the gears, ratios of the number of gears, you can get any rotation rate that you want. Okay, so you can get uniform motion. But as we said before, the motions of the planets and even of the moon are not uniform. So how do you get non-uniform motion out of uniform motion? Well, the antikythera mechanism uses the pin and slot mechanism, which, as far as we know, has no precedence and no descendants in the ancient world. So you have two gears, K1 and K2, and they have slightly offset centers, C1 and C2. K1, which is this dash gear over here, has a pin on it. K2 has a slot, a radial slot, that can hold the pin. Now K1 is driven at uniform speed. K2 is passive. It rotates only because it's being forced to rotate by the pin that's in the slot. Now you can imagine that when the pin is over here, then the pin is going to be closer to C2 than it is to C1. So that means that the same motion, so that means the same horizontal physical displacement of the pin is going to correspond to a larger angle for K2 than it does for K1. On the other hand, when the pin is on the other side of the circle, it's going to be farther away from C2 than it is from C1. So the same motion is going to correspond to a larger angle for K1 than for K2. So even though K1 rotates at a uniform rate, K2 is going to speed up and slow down over the course of one rotation. Now, that's already pretty ingenious. What's even more spectacular is that this mechanism exactly reproduces the epicycle model of Hipparchus. You can prove that the position of this pin exactly corresponds to the position of the planet when it's orbiting in an epicycle that in itself is orbiting the Earth. Now the proof is found in Carmen 2012. It's a very short proof. It's a very simple proof. And it's definitely well within the abilities of the ancient Greeks to come up with that proof. Okay, so that's how the antikythera mechanism works. The antikythera mechanism was the pinnacle of ancient practical astronomy, in the same way that Ptolemy was the pinnacle of ancient theoretical astronomy. After Ptolemy and the antikythera mechanism, there will be no more advances in ancient astronomy. Nobody will come up with a better model than the Ptolemaic until 1600 years later with Kepler. In the meantime, the achievements of the ancient Greeks, not just in astronomy, but in philosophy, in politics, in physics, in even religion, spread far and wide. They were widely admired and built upon by the philosophers in Europe, in the Arabic world, and even as far abroad as India. So in the 16th century, Kepler finally came up with something better. He came up with something better by starting from the Ptolemaic model and applying the theorems of ancient Greek geometry. So he started from the Ptolemaic model. He shifted the reference frame from geocentric to heliocentric. And then he tinkered with the geometric construction until his model could explain the observations of his day to within experimental error. Now, after this tinkering, he noticed that the thing that he just constructed was an ellipse. And thereby he came up with the laws of Kepler, that although the planets orbit the sun in an ellipse, with the sun at one of the two foci. Now, his work was only possible, first of all, because he had a Ptolemaic model to start as a basis. And number two, because he knew geometry. How did he know geometry? Well, he studied Euclid's Elements. This is the most successful textbook of all time. There are more editions of the Euclid's Elements than there are of any other book except the Bible. It's been basically in continuous publication from the day it was written in 200 BC until modern times. And until the 19th century, it was the textbook that everybody in Europe and the Arab world used to study geometry. It was also, incidentally, the beginning of axiomatized mathematics. It starts from 5 axioms. It builds theorems on the basis of the axioms, and it builds more theorems. It proves more theorems on the basis of the previous theorems and the axioms. This is the way that all modern mathematics is done. And it started with Euclid. Okay, so he knew geometry. That's great. You recognize that the final step of the process was that he recognized the thing he constructed was an ellipse. How did he know that? Well, because the ancient Greeks already extensively studied the ellipses. Euclid talks about ellipses. Apollonius of Perga and Hipparchus and Archimedes, they all wrote treatises on ellipses. So the ellipse was something that was familiar to all educated people who were educated with ancient Greek texts. That was not true for other civilizations, by the way. For example, like the Chinese were very good at mathematics. They never discovered the ellipse. The Mayans, they were also very good at mathematics. They never discovered the ellipse. Okay. Yeah, so that's all I have. Kepler was a great guy, but he wasn't the only great guy. He and Galileo and Newton and other people in the scientific revolution created a movement that continued until the present day. Their knowledge built upon prior knowledge. Science kept on advancing, and all of this created the modern world that we know and love and take for granted. Yeah, so any questions?
Questions? Well, I'll start with one.
Mm-hmm.
This Antikythera mechanism would have been a tremendous intellectual and mechanical challenge to actually construct. So,
yes.
And assuming there was only one or very limited production, are there any literary references from the time? I mean, if somebody actually built a thing like this and it works and does all these calculations, you know, and all of a sudden it's lost at sea.
Yes.
You'd think people would have noted that.
Mm-hmm. We do have one potential eyewitness account of the Antikythera mechanism from ancient times. Let's see if I can find it. Okay, Antikythera mechanism, Cicero. Okay, Rhodes. Okay, Cicero.
Cicero.
Yeah, okay, so maybe I won't find the exact quote right now. But like, yeah, Cicero was an ancient Roman orator and statesman and philosopher. And he wrote about the ancient astronomer Posidonius, who's from Rhodes. And he says that Posidonius had a device that showed the positions of the sun, the moon, and the planets. Now, the reference to Posidonius and Rhodes is especially interesting because we can look at the device and its workings, and we can ask for what latitudes is the device most accurate.
Mm-hmm.
And it turns out that the latitude, let me bring up a world map. Maps. Okay, so Rhodes is over here. It turns out that the latitudes that are most consistent with the device are from here to approximately here. Now, you realize that that excludes almost all of the Greek world. Most of the Greek cities are over here in what we now call Greece. There were a lot of Greek cities here in Asia Minor. There were a lot of Greeks in Alexandria. But between here and here, you have mostly ocean. So Rhodes is one of the few places where we know great ancient astronomers lived that's consistent with the latitude of this device. So yeah, very possibly this device was constructed by Pythagoreans, and Cicero had an eyewitness account of it. Now, the other interesting thing is, I think the same person, Cicero, he talks about earlier astronomers like Archimedes. He says that Archimedes had two spheres that also indicates the position of the moon, the sun, and the planets. Now, Archimedes was about a century or 2 centuries earlier than this device. We don't know exactly when this device was made. And so Archimedes was a native of Syracuse, and Syracuse was taken by Rome in 212 BC. And during the sack of Syracuse, he was killed by a Roman general, a Roman soldier, against the orders of the Roman general, actually. And the Roman general apparently took the two armillary spheres of Archimedes as his only loot from the whole city.
Oh.
Now, Syracuse was one of the richest cities of the ancient world. So you can tell how valuable these armillary spheres must have been. Yeah, so there might have been precedents to this device in the armillary spheres.
I was wondering how large is that device that was recovered from the shipwreck?
Let's see if we can have a scale. Antikythera mechanism. Scale. Okay, so 34 by 18 by 9 centimeters. I think that was the device that's recovered. That was a fragment that was recovered. Yeah, so maybe the original device was slightly bigger than that. So like maybe 40 centimeters-ish.
Okay, thanks.
Mm-hmm.
You've talked a lot about the Greeks.
Mm-hmm.
When you think of Roman science,
Mm-hmm.
per se, when you think Lucretius and the notion of the atom and so forth,
Mm-hmm.
but was astronomy particularly explored by the Romans, or the Romans just more practical and rather do engineering and do all the techniques and logistics of building big things rather than the theory?
Exactly. That you summarized the Romans perfectly. The Romans were the master engineers of their time. They could build roads that were thousands of miles long and like almost perfectly straight. They could build like gigantic colosseums and great cities, and they could drain like major lakes, right? So they were extremely good at engineering. But in terms of science, they basically didn't do anything. I mean, Ptolemy was technically a Roman. He lived in Roman Egypt, but he was ethnically Greek. And in fact, until the very end of the Roman Empire in 1453 AD, the culture of the Roman elite was Greek. They spoke Greek, they read the Greek classics, they learned Greek science and geometry, and they were very familiar with Greek history and even Greek myth. So yeah, there's a great saying by the Romans, which is Rome conquered Greece, but Greece conquered its savage conquerors. Now, Rome conquered Greece militarily, but Greece conquered the savage conquerors culturally and religiously and in every other way. Yeah, and by the way, the Romans were a very proud people. So like for them to say that another people were more civilized than they are, that's like a very high compliment.
More questions? Okay, I'm just loaded with ancient engineering questions. I ran across a reference just recently that talked about the Roman foot.
Mm-hmm.
And it was really, whose foot was it? I mean, these things are named after body parts. and it was
Right.
Marcus Vipsanius Agrippa's foot.
Interesting.
If
Wow.
this is correct, this is fairly late. Like, when did he die? About 12 AD.
Mhm.
And you mentioned the fact that the stadia were different depending on which city systems you used, but
Right.
one would think there would be more standardization
Mhm.
because measurements would be very important, if nothing else, for construction and materials and all kinds of practical purposes. But
Mhm.
do you know it? Have you run across anything about standardization?
Let's see. Okay, so like if you were a Roman engineer, I think like your units will be pretty standardized.
Mhm.
Yeah, like a mile in Britain would be the same as a mile in Syria. I think the thing with Eratosthenes, well, first of all, he didn't live in the Roman Empire, right? He lived in Ptolemaic Egypt, and like he was ethnically Greek, but he lived in Egypt, where most of the population was not Greek. Yeah, and like, okay, so Olympus was a very important cultural center for all of the Greeks, but he didn't live anywhere near Olympus. He lived in Egypt. So I think that's why the confusion comes in as to whether he would have used the Egyptian stadium or the Olympic stadium. And actually, it's kind of a moot point anyways, because if you look at his method of measurement, he got an accurate answer by coincidence. He got lucky. His various errors canceled out with each other. Because first of all, like how do you measure the distance from Alexandria to Syene? You basically have camels that pace back and forth and count the number of steps. That's not a very reliable method. And also, this calculation assumes that Alexandria is directly north of Syene, which is not actually the case. Let's see whether we can bring up a map actually. Okay, Syene. Is that city? Oh, it's Aswan. Okay, I didn't know that. Apparently, it's the modern city of Aswan. Okay, so Syene or Aswan is over here. Alexandria still has its own old name and is over here. And you can see it's like kinda due south, but like it's definitely at an angle. Yeah, and like maybe the cosine of the angle mattered. Actually, it seems small enough that it probably didn't matter. Okay, so maybe that's not such a big source of error.
Okay. I'm gonna another question.
Didn't the Arabs also have some major contributions to astronomy?
Yes, they did. Let's see. So I should go to the, okay. So we know Ptolemy's work as the Almagest. Why do we know it as the Almagest? Well, because Europe rediscovered this work from an Arabic translation. And why did the Arabs, why was it discovered from an Arabic translation? Well, because the Arabs were the greatest astronomers of the Middle Ages. Yeah, so the Arabs invented a lot of new astronomical tools that made it possible to take much more precise observations of celestial positions. They invented the astrolabe, which is kind of similar to the Antikythera mechanism, but like not as sophisticated. One Arabic astronomer discovered another type of lunar motion. I forgot what it was called, but he incorporated it into the Ptolemaic model. He managed to make more precise predictions of the lunar position. They also like greatly advanced trigonometry, which is a huge component of astronomy, as we've already seen with Aristarchus and Hipparchus. And they were especially keen on spherical trigonometry, because Muslims are supposed to pray towards Mecca, right? But we live on a spherical surface. So which direction is Mecca? How do you compute that? Well, you use spherical trigonometry. And since the Arab world was so big, it spanned all the way from modern Morocco to modern India. You know, it's like, it's a huge portion of the globe surface. So you really need to use calculations to find out which direction to pray to. Yeah, the Arabs were also very good travelers and traders and mariners. And to navigate, you need to use the stars. I think that was also a big driver to why they were so good at astronomy.
Is there intellectual crossover between Hellenistic astronomy? Now I remember Alexander the Great's going to India and Indian astronomy.
Yes, very significant crossover. So there were actually Indian astronomers. God, I'm going to butcher his name. Aryabhata? Yes, Aryabhata.
Ooh.
Okay, so this was a great Indian astronomer. Yeah, he mentioned the relativity of motion, which today we call Galilean relativity. And I think he also was the first person to, okay, so he advocated the heliocentric model. I think he was also the first person to, let me see.
Ooh.
Elliptical. Yeah, he was actually the first person, possibly, to believe that planetary orbits are elliptical rather than circular. And we know that Aryabhata, along with like pretty much every ancient Indian astronomer, they definitely lived after the ancient Greeks, like centuries after, and they definitely based their works upon the discoveries of the ancient Greeks. And that's not a criticism, right? Like every great scientist bases their work on what came before. Yeah, so there was huge crossover between Greece and India. And actually, okay, so this is a less accepted theory, but if you look at Pythagoras, so Pythagoras believed in the transmigration of the soul. That's something that people usually associate with Hinduism and Buddhism, right? Reincarnation. And Pythagoras was actually a contemporary of Confucius in China. So like all of these great philosophers were living at approximately the same time, within a few hundred years of each other. Whereas civilization by this time was already extremely old. The first Mesopotamian civilization began in like the 40th century BC. Egypt was unified in the 31st century BC. So by this time, the civilized world was already 2,000 to 3,000 years old. So what are the chances that all of these great philosophers sprang up like within 2 centuries of one another? So I think there might have been more intellectual exchange even between China and India and Greece. Like in the 6th century, then we have direct evidence for.
Very interesting. More questions? This is a fascinating discussion and a great presentation.
Very, very interesting talk. Thank you. Does Caltech have a history of science major?
A history of science major? I'm not sure. I think it probably does. So I know there are people here who major in history, and there are professors here who are historians. Yeah, so I don't know, but I think yes.
Well, if there are no more questions, I think we ought to give a huge round of applause for this great presentation. And if people think of something in the dark of the night and Yeah, or amidst the riots or whatever, can we funnel questions through Steve to you?
Yeah, sure. Feel free to email me directly. I'll stop sharing and give you my email
Okay.
to everyone.
Didn't see it. Oh, you emailed.
Oh no, I sent my email on Zoom chat.
Yeah.
Oh, it's on chat.
Michael, how did Steve recruit you to give this talk? Did you reach out to him? Did he reach out to you?
Oh yeah, he reached out to me. So what happened was I gave a similar version of the talk for the Caltech astronomy outreach lecture. So yeah, we have an outreach series where every month, like a new astronomer gives a talk on science. But I decided to do a combination between science and history. So yeah, that was like a pretty successful event. We had pretty good turnout. So Steve emailed me to ask whether I'd be willing to give another talk. No, he actually said the same talk, but he gave the time limit for this one as 45 minutes. For the other talk, it was 25 minutes. So that's why I added the stuff about the Antikythera mechanism. And I also added the stuff about Thales being an absent-minded professor. And what else? Oh, and the Pythagoras dying because he wouldn't like run through beams. And also the Pythagoreans discovering irrationality and thereby like disproving the premise of their own beliefs. I mean, so I've got to give some credit to whoever the Pythagorean was who proved irrationality. I mean, most people can't deal with that level of cognitive dissonance. Like imagine you have a religion you believe deeply in, and using like the very techniques of that religion, you disprove the premise, and you disprove it in a mathematically rigorous way.
So does this indicate that the Palomar docents and the people who tune into these Greenway talks have longer attention spans than the Caltech faculty and student body?
Oh, the Caltech outreach series is for the general public. So yeah, I think the general public probably has a shorter attention span. But yeah, I'm glad I got to talk about the Antikythera mechanism. Because like it's really like the most impressive device to come from the ancient world by far. We don't have any precedents. Like the Romans, I said, were very good at engineering. They never came up with anything similar. The Chinese, they were also very good at engineering, like not so good at science. They still believed the earth was flat until the 16th century. And like even then it was European Jesuits who came and told them, the earth is not actually flat. Yeah, they were very good at engineering, but even they didn't come up with the Antikythera mechanism. So yeah, it's a major exception to like my conception of history, which is the Greeks were very good at science, but not technology. And the Romans were very good at technology and engineering. And by the way, so I said the Antikythera mechanism probably came from Rhodes. There were actually two Rhodian astronomers who lived at about the right time to have made it. There's Hipparchus, who I talked about, and there's Posidonius, who Cicero talks about.
Well, thank you very much. This was really very enjoyable, I learned a lot of stuff.
Yeah, me too. It was the first time I did research, like deep research on the Antikythera mechanism, and I'm glad I did it.
The machining was terrific. There must have been other mechanisms.
Well, so there was like Archimedes' arbitrary spheres could have been a precedent. Yeah, so we know that that's not the Antikythera mechanism. First of all, because they were spheres, and second of all, because they were in Rome for a very long time. Like many centuries later, people were still referring to it. Yeah, so I don't think we know of any anything after the antikythera mechanism. And certainly the technology seems to have been lost. We don't know of any devices that incorporated, a complex gear train or the pin and slot mechanism.
When you think of Roman and certainly medieval construction techniques, it seems to be more geometric than it is numerical.
Yes.
And a
exactly.
device like the Antikythera, it looks like a mechanical computer that comes up with numerical solutions, ultimately, rather than, I know it shows relationships and so forth, but it's still a computational device. And it seems like they do things more with geometry and circles and and ratios and things like that. But I'm not sure.
Yeah, I would say that's like accurate, because by far the most advanced portion of ancient Greek mathematics was their geometry, and that was the only portion of mathematics that they investigated in a modern way, which is they come up with axioms, they prove stuff based on the axioms, and then they prove more theorems based on the previous theorems and the axioms. And in that very rigorous way, layer by layer, they built up to some very impressively advanced theorems. They discovered ellipses. Well, they discovered conic sections. Yeah. So the ellipse, the hyperbola, the circle. What else? They discovered and the parabola. They investigated 3D shapes like cones. Archimedes famously discovered the volume of a sphere and of a cone. They constrained pi in a rigorous way. What else? Yeah, and they invented trigonometry, partly because that was inspired by the astronomical research, because they needed it to answer astronomy questions. And their number system was not very good. So they didn't have 0. They didn't have our Arabic numerals, which are actually Indian, but they got transmitted to Europe from through the Arabic world. So I think the Greek number system had one symbol for 1, 2, 3, 4, 5, all the way to 9. And then a different set of 9 symbols from 10, 20, 30, 40, all the way to 90. And then a different set of symbols for 100, 200, 300, all the way to 900. And there's no easy way to do arithmetic using that number system. The algorithm we learned in grade school, if you add 2 numbers, you line them up, you add the digits, you add the carry, blah, blah, blah. That's actually an ingenious invention. It's not obvious at all that that's the proper way to add or the fastest way to add. And especially the multiplication algorithm. Why do you do it that way? Right? It's we get taught it, but we don't get taught why it works. And it's very difficult to invent from scratch, even if you have Arabic numerals.
Oh, very interesting. Okay, any more questions on this?
The word algebra sounds like an Arabic word. Is
Yes.
it an Arabic word? Algebra?
It is. Yeah.
And what does it, al usually means the in Arabic words. What does jabra mean? Do you know?
I don't know, but I can look it up.
The source of all knowledge, Wikipedia.
Yep, exactly. Okay, algebra, the reunion of broken parts.
Reunion of broken hearts.
I guess that kind of makes sense. You have algebra, so you don't know what X is, but at the end of some, process of algebra, you find out what it is. It's something like that. I don't know. Interesting. Algorithm is also from Arabic. A lot of things are from Arabic. Basically anything that starts with al is from Arabic. And algorithm I learned earlier, it comes from al-Khwarizmi, which means the man from Khwarizmi. And the man from Khwarizmi refers to a famous mathematician, Abu Jafar Muhammad ibn Musa. And he was so famous that, you know, the whole field of algorithms got attributed to him.
Well, thank you again, Michael. It was a terrific talk.
Mhm.
Michael, I imagine that as a student, the Caltech is not open for in classroom. Everything is still being done remotely.
Yeah, exactly. Yeah, I wonder if I can just sit in on a history class. I probably can, just by, you know, going to the Zoom link. Yeah, thanks. You've given me an idea.
Yeah, but how is that working out? You know, there's so many interactions that you miss, and conversations and skull sessions with other students, and there's a whole student life thing.
Mhm.
So how do you feel about it?
Yeah, it's definitely much worse than the in-person, you know, routine. Yeah, because like it's a lot harder to talk to people. I mean, you could like message them, you could arrange a Zoom meeting, but like it's just much more convenient to walk up to them and have an in-person conversation. Like the barrier, I guess, to the conversation is a lot lower. Yeah, and also like it's a lot harder to stay motivated because you're at home, you're right beside your bed, and like you're on your own computer. Like if you play games, you don't have office mates to look at what you're doing and shame you. I actually came up with a solution to that. Like every day I share my screen with a colleague and he shares his screen with me. So we can see what each other is doing. And I make sure like we're not slacking off. So yeah, that was a great productivity trick. But yeah, like online instruction is definitely not as good. I would say anecdotally, like for people who are already doing well in academics, who are like, I guess, good students, the impact of online learning is a lot less than for bad students. Like the ones who can't concentrate, the ones who, you know, have no idea what's going on. Those people are really hurt by, you know, being at home and not having a parent to supervise them often.
Maybe you and your colleague ought to trademark this slackers.
The anti-slacking tool, yes.
Who knows? This might be a big deal. I can think of a lot of companies that might want to have a slackers index, find out how many people are playing video games on company time.
It's the cyber version of a cattle prod.
The cattle prod. Yeah, it's like mutual cattle prod, like two cattle prodding each other.
Thanks again, Michael. I'm gonna say goodbye to everyone.
Yeah.
Nice to see everyone, even if we're not up on the mountain. I know.
Yeah.
Yeah, thank you so
Maybe
much.
this summer. Okay, thank you very much, Michael, for doing this and sharing your expertise and your obvious interest in all this. And I hope your career goes well. We're all pulling for you.
You.
Okay, bye-bye, everybody.
Goodbye.